Welcome to Ask and Learn.
Okay, so the question reads that when water is boiled at a pressure of 2 atmospheres, the heat of vaporization is 2.2 times 10 to the 6 joules per kilogram, and the boiling point is 120 degrees Celsius. At this pressure, a kilogram of water has a volume of 1 times 10 to the minus 3 meter cubed, and a kilogram of steam has a volume of 0.824 times, or 0.824 meter cubed. Compute the work done when 1 kilogram of steam is formed at this temperature, and B, compute the increase in internal energy of the water. Okay, so I'm just going to go ahead and write down what is given to us. So P equals 2 atmospheres, and L is equal to 2.2 times 10 to the 6. I think L is the proper symbol to use for this. So we're referring to kind of the latent heat associated with a phase transition. And then it boils at 120. So I'll make that look more like a 120 degrees Celsius. And for water, we can say the mass is if the mass is 1 kilogram, then the volume is equal to 1 times 10 to the minus 3 meter cubed. And then for steam, we have that if M is 1 kilogram, then the volume is equal to 0.824 meter cubed. So it takes up much a larger volume, which sort of makes sense. Okay, so now for part A. The problem asks us to compute the work done. And so we can use the formula work is done by the gas is equal to P delta V. And in general, it's the area under a PV curve during the process. But since this is all occurring at 2 atmospheres, then the pressure stays constant and the formula reduces to P delta V. So we can just kind of go ahead and plug in our pressure of 2 atmospheres and our volumes. So it starts out as 1 times 10 to the minus 3 meter cubed when it's water, and it ends up at 0.824 meter cubed. Before crunching the numbers, we need to also convert the 2 atmospheres to pascals so we can have our work in SI units. So 2 atmospheres, and then I like to write out unit conversions like this, times 1.01, kind of a lot of sig figs, probably slightly too many. Pascals per atmosphere. And then actually, I'm just going to not do that second part. So here's that. And then times our change in volume. So the final volume is the volume of steam. So that's 0.824 meter cubed. And then the initial volume of the water, which is very small. I'm just going to go ahead and write it like this. I'm kind of running out of room. And then this is all meter cubed. Great. So now we just need to compute that. And if you do that, you plug that into a calculator, you obtain that the work is 1.67 times 10 to the 5 joules. Great. Oops. I'll go back. And For part B, it asks for the change in internal energy. Delta U is always equal to the heat minus the work done by the gas. Kind of an energy conservation equation. And the heat associated with a phase change is ml. And it's positive because you have to add heat to boil water instead of for freezing, that might be negative, or that would be negative. And then yeah, so we still have minus the work done by the gas. So we can go ahead and plug everything in now. So the mass is 1 kilogram. L is equal to 2.2 times 10 to the 6. Oh, forgot to put units on that. So those units are going to be joules per kilogram. So I'll go ahead and fix that. Joules per kilogram. And then I'll write that here. Joules per kilogram. And then we just want to subtract what we found in part A, that the work done by the gas is 1.67 times 10 to the 5 joules. Our kilograms cancel. I'll just go ahead and write it like that. And if you plug that into a calculator, you get that equals 2.03 times 10 to the 6 joules. So just kind of looking at the magnitude of these numbers, you can see that the biggest contribution to the change in internal energy was made by the whatever heat was applied to cause the boiling, because the 2.2 times 10 to the 6 numbers is bigger by an order of magnitude than the work done by the gas. So the work cooled a little bit when it expanded, but overall the heating contributed most to the change in internal energy.